Welcome friends to the fourth lecture on module 2 on the course on risk and reliability of offshore structures. We are talking about lectures on module 2. We already completed module 1. Module 2 is focusing on reliability theory in general and structural reliability applied to offshore structures in particular. And now this is the lecture 4 where we are going to talk about error estimation. We already saw that reliability analysis are done in 4 levels. Level 1, which is a classical example of LRFD method, load resistance factor design method, and level 2 takes about one variable and circumscribe the reliability study with respect to that variable. Level 3 of course does the analysis of the complete problem. It involves integration of multi-dimensional joint probability density function of the random variable, which is extended over the safety domain. In this particular level, reliability is expressed in terms of reliability index, which also gives me the failure of probabilities. Level 4 of course includes the engineering economics into the whole analysis under uncertainty. It considers cost and benefit of construction, it considers maintenance applicable for repair and other studies. It of course extends the study to understand details of consequences of failure. Now level 4 talks about the probability of occurrence of an event which is undesirable as well as the consequences, and it also addresses interestingly the economic perspective of this. Therefore, in level 4 actually the reliability analysis is converged towards risk assessment. Okay? That is very interesting for us to realize and understand that we will be heading, because in the later module we will talk about risk assessment alone on offshore structures. There we will also talk about how risk assessment is bridged with reliability. Therefore, I want to give you an introduction to you here that when reliability analysis or any analysis talking about probability of failure is focusing on the occurrence of that failure event and parallelly the consequences if the failure occurs. With respect to the engineering economics in terms of economic perspective, then we actually call the whole analysis or analogy as risk assessment. So, reliability is converging ahead in an advanced stage of risk assessment, because it will also talk about the interest on capital etc., as told by SRE et al. 1967. Sensitive projects like offshore structures, nuclear power projects, transmission towers, highway bridges all fall under this category of level 4. Now, interestingly, although level 1 is still used in the structural design methodologies, level 2 methods are useful in evaluating the safety of a structure. So, one can quickly say level 1 is used as a design method, level 2 is used for assessing the safety of the structure, of course level 4 is going to include the consequences and economics. So, probability of occurrence of any undesired event. In our case, the undesired event is the non-fulfillment of the functional requirement of the structure or its intended function on demand. Okay? We are not talking about the structural failure at all in this case, please understand this. Probability of occurrence of any undesired event, consequences if the event occurs. The moment you talk about consequences, you must know whether it is going to talk about the human loss or it is going to talk about the asset management. So, it is very interesting that we include engineering economics into this. So, it is converging towards, as we just now said, path of risk assessment. So, of course, level 2 is interestingly useful for assessing the safety of the structure. Now, interestingly, this can also be used as a tool to determine the rational set of safety factors, that is very important. Level 2 can be also used to evaluate the rational set of safety factors. Okay. As we all know that the whole process is going to be under the circumscribing of probability theory. So, we now discuss about random variables. Let us say space of variables, let us talk about this. Space of variables actually refers to the characterization of the basic load and distance parameters. It actually refers to characterization of load and resistance. There are only two events here, parameters. Because these are the two events which are generally used to form the performance function. We already said in the last lecture what do you mean by a performance function and how do you assess this function to say whether the function is failing or safe. In simple terms, as said by Feisler et al. 1979, for n state variables, limit state function will be represented by n parameters. If all the loads or load effects, let us say, if all the loads are to be very specific, the effects caused by the loads or load effects be represented by, let us say Q, I write it here. Okay, let us say let all the loads or load effects be represented by Q. Let the total resistance offered by the system what we call capacity of the system be represented by R. Then the space of state variables is a two dimensional space. Two dimensional space, let us say, not state. We will try to plot it. I will draw the figure later. Now, the boundary between the domains, what is that? What are the two domains? Failure domain and safe domain. So, the boundary between the domains, that is safe domain and failure domain, there are only two domains here. Now, I may ask you a question, why there are only two domains here? Please understand, we already explained in the last lectures. As far as reliability analysis of offshore structures are concerned, it takes a binary value, yes or no, 1 or 0. Is it going to fail or is it safe? There is no third proposal except these two. Okay? I think this we have said in the last lecture. So, therefore, boundary between the domains may be safe domain and the failure domain. There are only two domains here, will be described by a limit state function. We call this function as g of, the function has got two space of variables. One is the resistance offered by the system or the capacity of the system, the total resistance offered by the system. Other is the total load or the load effects offered by the system, and we said that. Okay. Now, since both the parameters R and Q are random variables, we already said what is a random variable in the first module. How do you qualify a variable to be a random variable? We already explained this, please look back those lectures. One can therefore define what we call a joint density function. Which we can say as f R Q, the variables are R Q, because R can take any value between 0 to capital R, similarly Q can take any value from 0 to capital Q, and probability of failure, because we are interested in reliability about this because converse of this, is then calculated by integrating the joint density function Why it is called joint density function? Because it joins two parameters which are independent, exclusive and exhaustive. It connects, it bridges. So, joint density function over the failure domain. What is the failure domain? The failure domain is the region in which my function is less than 0, takes a negative value. Let us mark or draw the space of variables marking the safe and failure domain for two variables R and Q. R is the total resistance and Q is the total load. I am marking the space of variables basically they are only two variables R and Q, marking the safe and failure domain. That is what I am trying to do here. Okay. Let us say I plot the distribution and find the mean, which I call as mu of Q. Similarly, I try to plot the distribution and find the mean and say mu of R. Wherever they intersect, the domain will start from there, and let us say it can have any values in this region, so on. So, interestingly, the failure domain is the failure boundary, which is the limit state function which is r minus q is 0. So, obviously, this is my failure region. Because in this region r is less than q, take any value, q is greater than r, it means the load is much more than the capacity. And this is my safe domain, because in this domain r is greater than q, and that is the division which divides. So, that is a space of variables marking the safe and failure domain for two space of variables r and q, which represents respectively the capacity of the structure and the load effects on the structure. Both are random variables. Now, due to the complex shape of the failure domain that arises from the uncertainties of the variables, now these two set of variables r and q have lot of uncertainties, okay, contain a variety of uncertainties. We already saw them in detail. Now, one can ask me a question, what will be the consequence of the presence of uncertainty in estimating r and q? This will make the failure domain complex. Now, one can further ask me a question, if the failure domain is made complex, what is the difficulty, sir? This will cause difficulty in integrating the joint density function. That is the overall issue, that is the mathematical crux in the whole problem. Okay. You will not be able to easily evaluate the integration of the joint density function over the failure domain, because that is a requirement. I must be able to integrate the joint density function over the failure domain. Now, the failure domain will become complex. Why it becomes complex? Because the variables, first of all, they are random, okay, no problem, but they have lot of uncertainties. Now, the question is how this issue will be solved. Therefore, this issue is solved by representing or expressing structural reliability as a number which we call reliability index. Okay, that is how it is compromised. Now, obviously, if you are going to estimate the reliability, which is a qualitative issue, because uncertainties cannot be defined with high degree of precision quantitatively. So, it becomes more or less a qualitative issue, whereas when you move from reliability to risk assessment, it becomes a quantification issue. Okay? So, as on that level, let us say reliability is more or less a relative, comparable, qualitative assessment. When you are trying to compare two variables qualitatively, which are random in nature or arise from a random process, and they have lot of uncertainties inherently present which cannot be ascertained accurately, this will result in error. Okay? Now, let us talk about error estimation. Error actually is a departure from the acceptable practice with that of the results obtained from analytical studies. That is the error is. Okay? Error is nothing but a departure from the acceptable practice which is present in the analytical studies. What do they do actually? I mean, what would be the consequence, difficulty because of presence of error? They add more degree of uncertainty to the design and construction. Presence of error add more degree of uncertainty to design and construction activities. So, it is good that we must minimize this error. Now, let us see, can be mathematically minimized then. The basic reason of difficulty arising from this level is these errors what you are talking about, which are departure from the acceptable practice, are essentially human errors. Okay? Or the primary source, which are found to be one of the main reasons for failure. We have seen a couple of case studies also. Okay. One of the main reasons for failure has been seen from the human error. So, therefore, if structural reliability should be focused towards error control, it should deal with minimization of human errors. Now, errors are generally categorized according to the causes and consequences. There are two approaches to control errors. We have already said in reliability analysis, we already have uncertainties in R and Q, which are inherently present, we cannot eliminate them. Okay? We do not want to add further uncertainty, which generally arise from error, which is essentially or majoritarily coming from human error. So, therefore, reliability should focus towards controlling these errors. Now, there are two approaches by which you can control the error. One, can reduce error frequency. Alternatively, you can minimize the consequences. Which arise due to these errors. Now, let us classify the errors. We already said errors are classified based on the causes and consequences. Errors can be classified or categorized on the basis of causes and consequences, which may be useful in selection of efficient control measures. Analysis of causes are actually useful in identifying the occurrence mechanisms Therefore, one can plan to reduce the frequency of occurrence, which is actually the first way to control the error. Consequences of the error can be prevented. Can be prevented, or I should say minimized. You cannot prevent it because they will be always existing, by adopting special design procedures. We can name one very quickly. One could be performance based design. It can be one design approach which first highlights or emphasizes or pre-states what is the performance level required. Is it immediate occupancy, life safety, prevention, etc. What is that level required, and to that level what should be the material characteristic required to be used in the construction, what should be the preferable structural form, what should be the order of indeterminacy in the given system, etc. So, one can always first prefix the performance desired by the or fixed by the designer, then based on that one can always try to reduce or minimize the consequences from the errors which are inevitably present, because these errors cannot be eliminated, please understand, because they are originated from the uncertainties present in the variables R and Q, and these uncertainties which are present in the variables resistance and load are inherently and implicitly present, they cannot be eliminated at all. Okay. What we can do is, we can either control the error by minimizing the consequences, or we can control it by reducing the frequency of occurrence of these errors in the design procedure. Therefore, errors can be considered with regard to the person involved. There can be many phases by which you can categorize and, let us say, highlight or separate or group the errors. So, errors can be grouped based on or on the basis of: 1, the personnel involved; 2, phase of the construction process; 3, place of construction; 4, identifying the reason and the mechanism for occurrence of error. Based on that also you can group it. So, there are actually 3 fundamental types of errors. One can be errors of concept. They are unintentional departures from the acceptable practices. Why do they occur? They occur due to insufficient knowledge. The second error could be errors of execution. They are unintentional departures again from the acceptable practices. Which occur during execution, that is called execution errors. This may be due to oversighting, improper supervision, poor quality management, etc. There may be many factors. The third could be errors of intention. They are intentional departure from the acceptable practice. Why do they occur? They occur because of mistakes. In fact, I should also say lack of experience, etc. So, we are talking about error control which can achieve or which can able us to achieve the desired level of reliability, or on the other hand, to be very specific and simple, the required level of safety. Okay? Because reliability is actually converse of probability of failure, and safety is also more or less talking about reliability. There is a very good difference between safety and reliability which we discussed. I think you will be able to recollect them. So, to ensure reliability or level of reliability desired by the reliability engineer or the user, one should be able to control the errors. Either you can minimize the consequences or you can minimize the frequency of occurrence of these errors. These errors can be of three order. Two of them are unintentional, by mistake they happen. You can try to avoid them by imparting proper sufficient training, sufficient knowledge, capacity building, etc. Whereas the one which is intentional should be avoided completely by using or employing experienced personnel at all stages of construction of offshore structures, starting from planning, guidelines, layout, feed level, material selection, detailing, all at all stages, including commissioning and exploring oil. Till that level, at all stages, people should have dedicated set of experienced professional who already have a thorough knowledge of understanding of the whole scheme and process and all facets of the offshore structural project. Not only a construction engineer does not know about the design engineer does not know about the material choice, nothing like that. He should know, he should be thorough and through with all facets of this project. Then only one can minimize the consequences or avoid the occurrence of frequency of these errors in the whole system, which ensures the desired level of reliability or desired level of safety in the given project. We already said in the last lectures that reliability is also closely associated with what we call quality assurance. So, let us revisit back the same statement in a more elaborate manner. Interestingly, the solution of reliability problems can be applied at different operational levels. Okay. So, there are various responsibilities which are fulfilled through reliability as a tool on quality assurance. Let us say what are they? It involves various responsibilities like setting targets for reliability and quality assurance, coordinating the related activities, three, preparing guidelines and documents for that, four, development and operation of quality data reporting system, that is very, very important. Development of quality data reporting system. Okay. If these are all done, it can lead to solutions of safety assurance for systems under operation, what we call operable safety or operational safety, as discussed by Freudenthal 1947 and Dowling 1972. Usually, major part of the performance assurance is done at the first stage of design itself. Therefore, this is generally assured in level 1 of reliability itself. Why? Because most of these questions will be answered in the design stage itself. Okay. However, even the design stage, there are different levels of uncertainties which are inherently present in the design. How to handle them? Because uncertainties will improve or increase complexities in the whole process. If I am not able to address them in the design stage itself, they will propagate further and they will cause a permanent damage which can be seen as a consequence of those errors which arise essentially from the uncertainties present in the design stage itself. So, in the next lecture we will talk about what are those uncertainties which are inherently present in the design, how they can be handled or how are they handled suggested by various researchers, and what are those different tools or methods or theories by which this can be focused, so that the whole goal is to minimize error which essentially arise intentionally or unintentionally from the uncertainties which are present in the variables which are R and Q, where R refers to the resistance of the system and Q refers to the load effects or the loads acting on the system. Thank you very much.